to give a talk about my work with my advisor, Youn. Okay. Okay, yeah, sorry for interruptions. Yeah, so this talk is based upon this paper that was put out last month, and my collaborators, my advisor, and then I, Echo, and then about and okay, and I think well, everyone in this room knows what's Hubble law, but for completeness, let's start with this law, which says that galaxies moving away from us at the speed proportional to the distance from each other. And this proportionality constant is very important in cosmology because it is needed to estimate the size and age of our universe. Accordingly, there have been too many efforts to measure this Hubble constant by many collaborators and experiments. Where people realize that there are some clear discrepancies. There is rather like 4 to 6 sigma discrepancies between early universe data and late universe observation. And early universe observation comes from the ΛCDM, is changing pitch, and this is a small value about 63 kilometers per megaparsec. And the last late universe measurement come from the local measurements, such as from Conway or something like that. And with those give us larger value about 33 kilometers per megaparsec. And of course, there could be some unknown atomic errors, such as in the CND measurement or direct measurement. But as theory, we trust experimentally because they know their doing. So this could be a possible signature of new physics. So today, I want to explain this. So I want to try to solve this comprehension with dark vector physics. Okay, in order to solve potential with physics, we need to understand how CNB measures H star. And CNB measures H star by very tightly by measuring sound horizon angle. And this sound horizon angle is between this acoustic oscillation and this peak spacing gives you this sound horizon angle, and it can be expressed as sound horizon divided by the angular diameter distance. And angular diameter distance can be expressed as distance, and then for the sound horizon. And yeah, there are for the angular diameter from this is filtering. It is the time integral is say, and time of determination, and the sound horizon is the physics unit. It is from the zero or equation or time of recombination. So from those two expressions, you can determine H star, and we have this expression. And to increase H star, there are mostly three options. The first one is here to decrease the matter density at late time. This is called late time solution. And but there is some debate over whether it makes sense in the first place because data is mostly measurement error, but many less direct measurements tightly constrained is metal density and late times. So there is a problem about the late time solution, but I will go that but here. And the other option is change some speed and reverse. For example, you can change the considering by changing the alpha minus alpha or change the metal electron. But yeah, it's a little bit sounds a little crazy. So people are not that serious about this option. And the last one is increased metal density and order time. So this is what many theories choose. And also, I will take this test today. And as I said, there is you can increase metal density and order time. And one simple solution is adding that radiation and order time. But if the dark radiation is free streaming, there are two problems in this solution. That is the red effect, which means dark radiation is free streaming. Its personally propagation can just and very significantly suppress the peaks, acoustic peaks, and the position of the peaks. And also there's stable damping, which is caused by diffusion of photon. And so this is shown from stable damping. So without the stable damping or no photon diffusion, the acoustic insulation goes like this. But this damping comes from the photon diffusion. And same as this angle, which is given by this diffusion angle, which is given by the RD, the scale of the diffusion divided by the angular distance. And why we have stable damping when we add more and more dark radiation, because if we increase the Hubble tensor, Hubble constant, it is likely related to the diffusion scale, and also it increases diffusion angle XL, so there should be more diffusion damping when we increase by Hubble constant. And these drag effects can be addressed when we assume that the dark radiation is self-inflicting itself, such as self-inflicting neutrino. However, it still suffers from this example. And there is some better solution to this problem, which is proposed by this guy, Boston guy, and University, which is introduce a step in this density of dark radiation. But I mean is at some point, left redshift, there is some bomb step into dark radiation such that the higher L mode, higher L mode that entered the horizon earlier still left degree of freedom, while the low L mode feel higher degree of freedom, so we can increase the H naught. However, the high L mode, which suffers from stable damping, has less damping because of this step. And in this paper, the authors claim that they got gold medal in so-called International Olympics. So this model actually is researched by Planck data. Okay, then how can this text that radiation can be realized. In this type of model, there are multi-component dark radiation, which is interesting. So, for example, let's say there's dark photon, for example. So there's dark photon, dark fermion, and dark photon. So they interact with each other. And there's an threshold around EV scale. So here is EV scale. So below, above this red threshold, the degree of freedom in dark radiation is star and dark photon. And below that, there's only dark photon. Then, due to the conservation of entropy, there is a form that increase this and this around this net threshold. Yeah, this gives you this value density to solve to give a good fit to the Planck data. Okay, so far we have some solution to Hubble tension. So now we move to some another tension that is called SA tension. Okay, there's SA tension, which is minor. It is a level of 2 to 3 sigma, and SA is defined by this times omega m. And sigma 8 is some the amplitude of linear amplitude of relativistic fluctuation on the scale of 8 with respect to h. This corresponds to a lot of legal scale that can be the picture simulation of data. So, as in Hubble tension, there are many observations and efforts to measure this sigma over SA. And there are also some wider is some discrepancies between universe and universe level. Of course, early universe data come from the MVP to PAcDM, and this is point 3 value. And for the main measurement, it is 0.76 value. And there are some claims that it is more likely that there are some unknown systematic errors. And also this is very mild. Or it is not mild because it's 2 or 3 sigma. However, most efforts to solve extra tension worsen tension as well, because with a fixed decoupling, the relative decoupling, if you increase the density of radiation, it will increase the density of matter. So, which then there are more cranking of the dark matter. So, this tension becomes worse. So, this tension could be another signature of the physics. So we want to solve tension as well as tension. So to solve the situation where dark matter clustering itself, when there is only cold matter, we impose the dark matter interaction with dark radiation. So since dark radiation is also for inverse, the interaction between the dark matter and dark radiation gives more pressure on dark matter clumping. So we can prevent this. We can reduce this dark matter clumping. So this can be helped as a tension. And of course, there are two types of dark matter interaction and dark radiation. The first one is with case, and the other one is case. And this work, we focus on tightly case because there are more interesting features because of the interaction between dark matter and dark radiation.
So what again, you have EV right now, so whatever particles or dark matter. And then now you have dark matter. So what's the mass scale of the dark matter? It does not matter.
It doesn't matter. Yeah.
Just all you do is to diminish the pressure.
Yeah, that's right. Yeah. 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 Only the fraction of the dark matter, which is interesting matter, and then okay, then let's give some illustration how this that type to calculate dark matter and dark radiation work. So this is the scenario, picture that show you where there is only dark matter, entire dark matter is full dark matter. In that case, the dark matter, full dark matter, is floating because there is only gravitational potential. Now, let's say there is actually, let's say the dark matter is consists of cold dark matter, and there is some fraction of interacting dark matter. In the case, the interaction between the interacting dark matter and dark radiation gives pressure outside its potential world. Then this also creates some so-called dark acoustic oscillation in the photon and baryon fluid, and it gives this signature on the matter power spectrum. And also, as a result, there is shallow potential between potential and flow damping, so it can eventually structure as well. So this kind of solution is that curve here is called partially acoustic dark matter model. So in this model, this dark radiation is absorbed, and on top of that, there's interesting the component of dark matter.
So that's different from the folder.
Yeah, it is different from the
Yes, but it's not coming to the bottom. Kind of.
Yeah, there's a cold dark matter is on top of that, there's interesting dark matter is different from that. So this is why it is called partially acoustic. Okay. And this is the photon, and it is fermion, and this intrinsic dark matter is dark radiation. You can think of this high as dark photon, and this is dark electron, and this is dark photon, and in the model, the dark matter, the proton and electron is very tightly coupled. So actually now, even though there are some interaction between those things, this is very it gives very strong interaction. Then because of this interaction, the interaction rate, momentum exchange rate, in proportion to the temperature scale. So the ratio between the Hubble rate and the momentum exchange rate is almost the same. The ratio doesn't change, it's the same. It is very large interaction, momentum interaction. So because that, we have this shallow potential and slow current and like that.
Just to understand, why gate cannot be your interacting source? Why gate cannot be your interacting source? Because everything is dark. So I can have do you really need to for the state you need two dark radiation?
Yeah.
Oh, and so it
Okay. Okay, then we have some ingredients to solve both problems, like HDR and adaptation. So by that radiation, we can increase the radiation measurement of HDR. And using this PAcDM scenario, we can decrease the early measurement of SPartAcous. However, this model have some problem because just simply increase the back radiation will worsen or increase early measurable essays because they are more density. And this PAcDM actually decreased at a very low because as we saw in this rate plot, this just go down below after this definition. So we need some cutoff to give a better number to escape. So that's why this combining this PAcDM and PAcDM to work better, which is called partially acoustic dark matter, or it is a little pun, but it's called SPartAcous. Yeah, so this could be a mistake in cosmology for Hubble tension and large scale structure. So let me summarize our model. So there is on top of the cold dark matter, there is interesting dark matter, which just with dark radiation. So as I said, you can think of this as dark proton and dark electron and dark photon. And there's some cutoff. There's cutoff here. So it's easy about the decomposition time, and this is the Lagrangian for this field. As I said, around below this mass threshold, there is form of an effective to help solve HEPEC tension. And because I said that if there is no cutoff, this rate just go down below, just with too much pressure on dark matter. However, because of cutoff, it drops exponentially after this cutoff. So it presents to the tension. So by this, you can solve H0 and sigma 8 or SA tensions. And this is actually what happens if comparing to PAcDM. And so this is the actual better density. This green line shows the ΛCDM green line, which means there's no intrinsic dark matter. And this blue is blue and red line corresponds to the cold dark matter, and this cold dark matter is this intrinsic dark matter. And this dashed line, the cold dark matter and intrinsic dark matter, PAcDM. And as you can expect, the cold dark matter, this ΛCDM line has more flanking. There are more metal fluctuation, and it's hard to see, but this solid line is a little bit higher than PAcDM. So this SPartAcous model gives you less metal fluctuation because there is pressure caused by that acoustic oscillation. And after this cutoff, this IDM to follow this cold dark matter clocking because there is no pressure because of the inflection, and there remains only the gravitation inflection which will remain. However, for PAcDM, there's no such cutoff, so just clumping here. Yeah, you just have the metal fluctuations. And so this case, so the difference can be expressed between, but in this Lagrangian, so for PAcDM, there is no cutoff, as I explained. Okay, and this is the actual better power spectrum compression for PAcDM and SPartAcous scenario. And now we we vary the fraction at chi is the fraction of intrinsic dark matter, and if fix the delta ineffective it's just 0.5 to the mean by the integral delta ineffective, and this value is the redshift of transition, which is proportional to the length of the dark electron. And as you can see, this solid line for the PAcDM, and this line is for the PAcDM, and there are much more operations. There are much more complex operations for PAcDM because there is no color in the integration. And you can see same thing when you vary this color redshift with the F chi and delta 50 and from values. And you can see because of that oscillation, there is this figure. We can see a better further feature estimation. This type of oscillation can give you some signature on this type of model.
The power spectrum of the sum of this controlled by matter plus the everything divided by 5.
Yeah, it's divided. Yeah, it is with respect to other. With respect to ΛCDM predictions.
1% or 5%.
Yeah, this is 1.5%. This is yes, 1%.
So when you run the decision through CMP faster.
This actually goes in black.
Okay, yeah. So when you like is the matter, the omega matter is like the sum of what's interacting, and that sums to like whatever the full is.
Yeah.
And so the universe is still like black.
Yeah. Yeah.
5% of
But omega matter is like the measure state. Omega matter is
yeah. So
oh no, I'm just trying to understand like what's the calculation.
okay, so I'm almost toward the end of my talks. But this is what and so for this is our prediction of H Hubble constant changing the redshift, and this is on the beginning. Yeah, so this is another temperature redshift. And this is our best fit yet because we are doing fluorescent change color spinning. So we don't have the complete answer yet. This is what we think.
So what's the going on centimeter measurement? Is it centimeter or fold? At the equal to 20.
I
Oh, so it's a 3,000.
yeah, 3,000
Oh,
something.
so that's the number.
Yeah.
Okay, so then, so,
No, this is our prediction.
oh, this is your, so what's the 21 centimeter?
So I tried. Yeah, I tried to find that. And yeah.
I somehow I thought it's around 2,000 or 2. Yeah, just kidding.
Yeah. Yeah.
So, but you have a prediction for that.
Yeah. Yeah. We can do for data when to perform.
Actually, that's a clean. For the almost a meter. Actually, I don't know that. I actually. Oh, you mean it's with the edges?
Yeah.
I thought that was supposed to be.
Oh,
Anyway, it doesn't matter. It's all the same.
But what's the opposite?
That I don't know. Okay, yeah. So I feel like I should.
Okay, so as conclusion, this identified attention could for new theories beyond the non-SPartAcous and here,
Sorry.
that feature and that matter and that creating picture and that here, perhaps there are some if we put those models together, we can have a better model which is promising the fact that we can have some degree in inclusion, so it's like nature and you have information on the content. And we just totally follow anything on the information. And we have that it can have so pretty with sure, not crash.
Okay, so we have plenty of time for questions.
Taewook,
Yes.
the page 42.
For this one?
Yeah,
For
just a simple question about the F sub chi. Is the fraction of dark matter chi compared to entire dark matter? Correct?
yeah, it is 5% of total matter. Is
Okay.
interesting.
And that your scenario, what would be maximum fraction you can get?
We from the data, we see the 5% is almost the maximum value we can allow for interacting dark matter in this scenario.
I see.
Yeah, so this is almost 5% is almost maximum of the friction we have.
Thank you.
Does this answer the question?
So like, if you compare to like power spectrum measurements for large scale structure, like the 0.6 are probably already filled out, right? Will you plot like the matter power spectrum?
Yeah, sure, yeah. So
So this is just,
yeah, sure, yeah. We should implement it.
yeah, so okay, so you're not like, okay, so
You need
there's like 5% or so that's kind of just too big.
Yeah,
from,
too
like-
big, yeah, so actually, benefit is about 3% or 1% or 150. So
Yeah, I found that. Okay, so that's part of your, okay, so your last plot, when you show your result,
Yeah.
that all that stuff goes in.
Yeah.
All that data. So the data you're using is like large scale data, CD data.
yeah, think they are MBA or MBA or these are, yeah.
Other question? Okay, sure. I have a question. So I guess you mentioned that so here the species chi is not dominant dark matter. So just
Yeah, just
one component.
one component. Yeah, there are dark electron, dark protons. Yeah, but they are very small.
Yeah. So okay, so the dominant cosmological dark matter is sitting somewhere, and then so you're playing with the sub-components.
Yes.
Dark matter. So the chi is interacting with the psi to dark open exchange. So you didn't specify the other mass scale of the high, but what would be the sort of the prefer?
Yeah, there's some. Yeah, you activate my segments. So, there are some things we investigated. So this and high and what? Yeah. So this line there's density filter and this is there is some kind of thing we are allowed because there are many calculations and this is our base measurement. So this is 1 TB. So we are thinking of the 1 TB is thinking dark matter
Okay, but basically, this white region is sort of allowed.
Yeah.
I mean, it's not constrained by the other.
Yeah.
And then, so I was wondering whether your model would give rise to like a boosted dark matter in the universe. Yes. So now I guess you know the psi is very large,
Yeah, I say that.
right? So now, what 5% of the dark matter is, let's say, you know, is chi,
Yeah.
right? And then it is chi, I definitely quote that. And then maybe they emulate you know, the psi through the exchange of the dark matter.
Yes.
And then the psi is very light. So I guess you know, the psi could be very energetic.
Yes.
Right? So then maybe some neutrino experiments or in the other experiments would observe the psi.
But in this model, there's no direct connection between standard model and dark matter.
Oh, so this dark photon doesn't interact with the standard model.
No, yeah.
It's purely the.
Purely.
Pure dark, yeah.
So your gravitational, maybe there are some boosted things going on in the dark center, but you.
Okay.
Why do we need
Oh, I see. So then, so if you allow the dark photon to interact with the standard model particles, then so your picture is completely ruined, or
So,
a lot of constraints?
yeah,
a lot of
yeah, but I don't think, yeah, that's it. Yeah, I don't think, yeah, I was.
They are hiding. for some reason.
I see. I see. But what if you know psi only couples to you know standard amount of particles, those other particles, so like you know these are
Yeah,
photon.
then,
Is this still
But he has to solve that state.
so that reach the other picture? So the psi also should be completely in the dark sector.
Because he's picking up that solution from new minus paper,
Hmm.
and that paper shows that you need 2 degrees of freedom to have that gravitational sector in variable state. And he's bringing
Oh.
about
Okay, so the gravitation, okay, purely gravitational,
because his aim is purely the
right? So once you tunnel non-gravitational
number of.
right. I see. I see. Okay. So, any further questions for you? Okay, so let's thank the speaker. Okay, so so Taewook is gonna just stay with us. So, questions,